Okay, so time is approaching and we are starting our afternoon session with the online talk by Professor Bas Lemmens from University of Kent. I think that you may begin.
Okay, well, thank you. Thank you very much for this invitation. It's been really nice to participate in this event, and a real pity I can't be there. It looks absolutely smashing there. Okay, so my talk is about Hor function compactifications, something we've already seen a lot in this conference. And actually, I would like to discuss sort of the global topology and the geometry of these compactifications and show you that there's a link with duality. Okay, so just to make sure we're all on the same page, let me begin by just recalling the Hor function compactification, and I'll follow basically the setup done by Rival. So we start off with a metric space. We fix a base point B in our metric space, and then we're going to embed this metric space in the space of continuous functions on M, and we equip it with the topology of pointwise convergence. And then we realize that inside this space of continuous functions, there's the set of Lipschitz 1 functions which vanish at B. So evaluated at B, we get 0. And actually, this is a compact subset of this topological space, topological vector space. And indeed, there are many ways to see this, but actually it's a basic consequence of Kuratowski's theorem. Okay, it should also be said that actually the topology of pointwise convergence on this set of Lipschitz 1 functions is actually the same as the topology of uniform convergence on compact sets. Okay, so what we're going to do is, as I said, we're embedding this M into this space of continuous functions. And so we're going to associate to each Y in M a function, which I'll denote by H sub Y. And this H sub Y evaluated at X is nothing else than the distance between Y and X minus the distance from the base point to Y. Okay, and so in this way we get an embedding, and you can actually show quite easily that that's just actually a consequence only of the triangle inequality of the metric, that H sub Y is in fact a Lipschitz 1 function, and clearly it vanishes at B. Okay, so in fact, I could have done this setup not with a metric space, but something, our distance just has to satisfy the triangle inequality. It doesn't have to be non-negative, it doesn't have to be symmetric. Okay, but for our purposes, we'll take it to be a metric space. So, so we have this embedding of our metric space into this compact set, so we can take its closure, and that closure will be called the Hor function compactification of M. And of course, the boundary is called the Hor function boundary, and the elements in this boundary are called Hor functions. Okay, so this is not always a proper topological compactification, as our embedding need not have a continuous inverse on the image. And the point is that this is the case if our metric space is actually a proper metric space. But in general, one cannot hope for this. Okay, so in our context, actually, we will assume that our metric space is proper and geodesic, meaning that the closed balls are compact and there's a geodesic segment connecting any 2 points in our metric space. Now, in that case, actually, the topology on this Lipschitz 1 space is actually metrizable. And so any Hor function is actually the limit of some sequence in our metric space rather than of a net. And so there's a fact that actually to get a Hor function, you can consider a sequence, and this sequence is forced to run off to infinity. Okay, so you cannot create any Hor functions by obviously letting Yn stay inside or stay bounded. Okay, so in general, it's quite hard to compute the Hor functions, or to even to compute all Hor functions and to get an idea of the Hor function boundary. However, in some nice domains, in nice metric spaces, one can say one can do this. So we've already seen several situations. So like we can consider domains in Cn with the Kobayashi distance. Well, if we would take our domain to be the Euclidean ball, then these Hor functions are given by this h psi, where, well, this is the logarithm of this ratio, where psi is just a point in the boundary. So at each point in the boundary of the ball, I have a unique Hor function given here, and these are all. Now also you can actually do something more general, namely you can look at products of balls like this, so you get general sort of polydisks. Then actually the product property of the Kobayashi distance allows you to actually show that quite easily that the Hor functions are given like this. So h of z is the maximum over j in some index set j over these functions h xij evaluated at zj. Zj lives in the ball b and j minus some constant alpha j, where this constant is non-negative. And so these h psi j's are just these Hor functions up here. And the alpha j's are non-negative, where we require the minimum to be 0. And the psi j's obviously live in this boundary of this ball, and j is just some subset of the indices we have. Okay, so that's quite explicit. Let's do some other examples. So let's take a Euclidean space, or real Euclidean space here. Then all Hor functions are in fact linear maps. So they are linear functionals. And indeed, you can easily find them. Basically, h of x is minus the dot product of eta with x, where eta is a vector of norm 1. And this Hor function you would get by running along the ray through eta off to infinity, and that gives you exactly that Hor function. Now you can take the maximum norm on Rn. This is something different, but it's like the Kobayashi metric, has a sort of product structure, product property. And you can see here that the Hor functions look very much like this, the ones you saw for the Kobayashi distance on the polydisk. Yeah. So here you get the maximum over j again, now plus minus xj minus alpha j, where j is again an index set, non-empty, and the minimum of the alpha j's is 0. So these are all non-negative, and the minimum is 0. So for example, if I would go along the diagonal here, like along this ray, I actually pick up this Hor function. This is quite easy to see. Okay, so we've also discussed in this conference Hilbert geometries. Now just a brief reminder. So a Hilbert geometry is a metric on some omega, which is a bounded open convex subset of some real affine space. And so the distance between x and y, well, to compute that, you determine, you draw the straight line through x and y, you identify these endpoints in the boundary, and then you take the logarithm of the cross ratio formed by those 4 points. And that's the Hilbert distance. And so Hilbert actually observed this in a letter he wrote this to Klein. And so this actually generalizes Klein's model of the hyperbolic plane or space. If you would take an ellipse, you would get actually the hyperbolic space. And then if you would take actually a simplex, we've also discussed that here, you get something which is actually isometric to a normed space. If you take the two simplex, your normed space is just a norm whose ball is a hexagon. Okay, so these Hilbert geometries are interesting because they interpolate between normed spaces and hyperbolic space. And where things get nasty is exactly where, rather than being a polygon or something strictly convex and smooth, you have flat parts and curved parts. And that's actually where the difficulty lies. Okay, so let me then, in this talk, specify one non-trivial Hilbert geometry for you. I'll work with that one throughout. And that one actually displays all the features, well, not all, but many of the features that actually are subtle in this analysis. And this is actually what I do is I'm going to look in the real vector space of n by n Hermitian matrices. And I assume that they're positive definite, meaning that all their eigenvalues are strictly positive, and they have trace n. So basically, I can look actually at the cone of all positive semi-definite Hermitian n by n matrices, and I slice that with the hyperplane of trace n matrices. This gives me a nice bounded convex set, and I take the relative interior of that, and that's this set omega Herm n. And actually, it's nice here. This is basically due to the Jordan algebra structure of this space, that actually the Hilbert distance you can express in terms of the spectrum of the elements. So here the Hilbert distance between A and B, so A and B are both positive definite matrices, so they're invertible, is actually the logarithm of the maximum eigenvalue of A times B inverse plus the maximum eigenvalue of B A inverse. Okay, so this is a way to compute things, and this can be actually done in a far more general context of Jordan algebras. Okay, so again, we can compute in this case the Horo functions explicitly. And namely, what we can do is we can take the base point to be the identity matrix, which has trace n, obviously. And so the Horo functions are given like this over here. So they're the logarithm of the maximum eigenvalue of B A inverse plus the logarithm of the maximum of the eigenvalue of C A, where B and C, so this is the data we get, we pick up these B's and C's, and B and C are positive semi-definite matrices, which actually are in the boundary of our cone, yeah, which actually have spectral radius both 1 and who are in some sense orthogonal, namely their Jordan product is 0. Okay, it's also to say that the trace of this of BC is 0. Okay, so really what we should think about is actually these B and C's are actually in the boundary of our cone, and they're in opposite faces of this cone, and they are normalized to have spectral radius 1. Okay, and this can be done in the general context of Euclidean Jordan algebras. Okay, so all these distances, they are examples of Finsler distances. So for me, a Finsler distance on a smooth manifold, it's just a distance that has an infinitesimal form. So f on the tangent bundle, such that the distance is actually expressed as an infimum of lengths, which are given by this integral, where this integral, the infimum is taken over all piecewise smooth C1 paths connecting x and y. Okay, so as we know, the Kobayashi distance it has such an infinitesimal form, but also obviously a finite dimensional normed space has such an infinitesimal form, namely in each of the tangent spaces, you just place the norm of the space. So here the norm does not vary, does not depend on x at all. Okay, but also the Hilbert geometry is known to have a Finsler distance. And let me spell it out what the infinitesimal form is in this example we have. So in this case, if we look at the tangent space at A, so A is invertible in the direction of B. So B is just an n by n Hermitian matrix. So then actually what we get is we look at the diameter of the spectrum of BA inverse. Okay, I can take A inverse because A was invertible. Okay, so this is again a nice way of doing things. And okay, so as I said, I'm interested in understanding the global topology and the geometry of the Horo function compactifications of these spaces, and somehow a guiding theorem in the Riemannian setting is the following well-known fact. So if we have a complete simply connected Riemannian manifold of non-positive sectional curvature, then actually the Horo function compactification of M is homeomorphic to the closed unit Hilbert ball in the tangent space at the base point. So So in that case, in the tangent space, we always have, because we're Riemannian, we have a Hilbert ball. And basically what we're doing to this metric space, we add basically a big sphere at infinity. And this sphere, it's naturally homeomorphic to the Hilbert ball in this case. Okay, so this is work, I guess, goes back to Eberlein and O'Neill. Okay, so what do I want to do? Well, I want to look at smooth manifolds. We have a Finster distance such that the restriction of our infinitesimal form at the tangent space at the base point of our Hor function compactification is in fact a norm. And I want to ask myself, what can I say now about the global topology and the geometry of the Hor function compactification with that result in mind of this in the Riemannian case. So now more specifically, and this is where duality comes in, I want to look at the following very explicit question. So you can ask yourself, when do you actually have a homeomorphism from the Hor function compactification of such a manifold onto the closed dual unit ball of the norm in the tangent space at the base point B. And this homeomorphism, it should map each part of the Hor function boundary onto the relative interior of the boundary face of this ball. Okay, so now there's several things I need to explain here, these highlighted yellow words. So first of all, you can say, Bas, why on earth are you insisting on this dual ball? Here, all balls are homeomorphic. What's the point here? Well, the point here is actually that the duality comes in because I want to understand the geometry. And this geometry actually has to do with this second part of my requirement, namely that each part in the Hor function boundary should somehow correspond to a relative interior of a boundary face of this ball. Okay, and now, of course, what are these parts? That is a thing I'm going to explain in a minute. But roughly speaking, is what you should think about is that a nice smooth manifold with a nice Finster distance, actually the Hor function boundary can be partitioned in a natural way into pieces. And these pieces actually are called parts, and they should correspond to this to these boundary faces of the dual ball. So that is, I hope this sort of motivates why I insist on this duality, and you'll see that this actually appears naturally. Okay, so let's talk about these parts then. Okay, so first of all, there's special Hor functions. So we all know that when we run off along a geodesic to infinity, we get a Hor function, and these are usually called Busemann points. But you can do something slightly more general to generate Hor functions. You can actually take a sequence which runs off to infinity, and you can take what is called an almost geodesic sequence. So what's an almost geodesic sequence? It means that, roughly speaking, you're close to actually making triangle equality in the end. Yeah. So for each epsilon, actually, I have that. Actually, if I look at the distance between xn and xm, and xm and the starting point of our sequence x0, and I subtract the distance from xn to x0, this is smaller than epsilon for n greater or equal than m, sufficiently large. Okay, so it means that I start making triangle equality, and I get sort of geodesic behavior. Now, Riefel already showed that such sequences always lead to Hor functions. Okay, that's an easy exercise, but it's useful. And in fact, Riefel asked, when are all Hor functions, when do all Hor functions come from almost geodesics? Yeah, so these Hor functions that come from almost geodesics are called Busemann points, and you can ask yourself, when is it the case that all Hor functions are Busemann points? And this is not an easy problem. And even in finite dimensions, finite dimensional normed spaces, there are norms where not all Hor functions are Busemann points, and in fact they are characterized by work of Cormac Walsh, who is in the audience here, and also in the context of Hilbert geometries, it's well understood when when all Hor functions are in fact Busemann points, again by work of Cormac. Okay, so we have these Busemann points, and they are in some sense much better behaved than just all Hor functions. And in fact, we can put a distance on this on the set of all Busemann points, where potentially the distance between 2 points can be infinite. Okay, so we allow infinite distances, but everything else is the same as normally what you would expect for a distance. Now, I'm not going to give the definition to you, but what I will do is I will tell you how to compute it and how to work with it. Okay, so given 2 Busemann points, h and h prime, and suppose we have this almost Ud6 xn converging to h. Then we can compute what is called the D2 cost. And that's actually this limit. So it's the limit of the distance from xn to the base point minus, or sorry, plus the Hor function h prime evaluated at xn. Okay, so what is in the picture? We have our sequence xn going is on the red line here, going to h. And then we have also, it's like a double limit. H prime is also comes from some almost Ud6 sequence, say xk prime. And we're going to look at basically the difference of the sum of the 2 red lines and the yellow lines. Okay, so we add up the distance on the red line and then subtract the distance on the yellow line. And now we're going to push this xk prime towards h prime, and we get a number. Okay. Now this number can potentially be infinite, but it does exist, and it's independent. Actually, can be shown to be independent of the almost Ud6, as long as we have these Busemann points. Okay, and then we can symmetrize the thing, and so we have the D2 distance, which is just this symmetrized version. And this is actually a metric on the set of Busemann points in the Hor function compactification. And this was actually constructed by Akian, Gobert, and Cormac Walsh. Okay, and this is a powerful tool. Okay, so now that we have this D2 distance, we can say we call 2 points equivalent, obviously, if this distance is finite. It could be infinite, but we assume it's finite. And then this partitions the whole Hor, this partitions the set of Busemann points in the Hor function boundary into equivalence classes. So, and these equivalence classes are called the parts. Okay, so the Busemann points have a natural partitioning into parts. Okay, and so in spaces where all Hor functions are Busemann, the whole Hor function boundary is partitioned into parts. So let's take the plane with the maximum norm here. Okay, so it's quite easy to see if you go along a horizontal line, a ray, you pick up the same Hor function, namely this one. However, if you would take 2 northeast diagonal rays and you start at different heights here, you pick up 2 different Hor functions, namely this one and this one if you would start at 0. And you can compute quite easily that the D2 distance is 1. Okay, so these are 2 different Hor functions, but somehow their distance is 1. Okay, so we can do this more systematically. If we would take R2 with the maximum norm, then really we could go horizontal along horizontal rays in the plus direction, in the minus direction. That gives us these 2 points here in the Hor function boundary. And we could go vertically up and down, gives us another 2 points. And then for each quadrant, each diagonal, so we have northeast, we get 1. Yeah, then we get northwest, we get 1. We get southwest and southeast. So in total, there are 8 parts here, and they sort of look like an L1 ball. Okay, so of course L1 is completely in the plane isometric to the maximum norm, but I hope this picture already gives a hint that duality might come in. Okay, so okay, so what's the strength of this detour distance and detour metric? Well, really, what you have is that actually any isometry on your space extends as an isometry to the Hor function boundary in case all Hor functions are Busemann points, yeah, with respect to the detour distance. And the way you do this is really, well, how would you define the image of the Hor function? Well, that should be the Hor function h, yeah, evaluated at the inverse of z minus h evaluated at the inverse of the base point. Of course, we want it to be 0 at b, so that's why we have this term there. Okay, so this allows one to actually analyze isometries of your metric space by actually pushing it to the Hor function boundary and seeing what the action does on the boundary. And this has been very useful. So this work actually allows one to actually analyze isometry groups of metric spaces. Okay, but that's a whole subject of a different talk. So let's think a bit about our domains, and let's go back to the Euclidean ball, where we had these Hor functions given like that, and it's quite easy to prove actually that they're all Busemann. In fact, in this case, they actually all come from even Ud6, not even almost Ud6. Okay, so all of them are Busemann. And now suppose we have another Hor function h prime. So now the data is an index at j prime, eta j on the boundary, and the beta j's. Okay, well, these are in the same part, so their detour distance is finite if and only if j is equal to j prime. The psi j's are equal to the eta j's. But potentially the alpha j and the beta j can be different. That's the only thing that can be different. And in fact, in that case, you can compute the detour distance, namely it's the variation norm of this vector. So it's the maximum of the difference between alpha j and beta j minus the minimum of that difference. Okay, so it's like a variation norm. So in fact, what we see here, that actually on the boundary, the Hor function boundary, it has these metric spaces that are isometric to a normed space here. This is nothing else than a normed space. It's r to the j with a variation norm, a quotient of r to the j with the variation norm. Okay, so now of course, what do we have? We have our domain here, which is a product of these balls, and then we know that the infinitesimal form at the origin is just given by the norm coming from this ball. Yeah, so this norm has open unit ball B, which is nothing else than the maximum of these thing, because it's a product. Yeah, to be in here, you need to have the maximum at most 1. So the dual ball is like an L1 over this product. Yeah, so I sum this. The requirement is that I have sum at most 1. And this has some relatively open faces, which are given as follows. Well, these are convex combinations, strictly positive convex combinations of vectors P, which I denote by P psi j. Yeah, where j is some non-empty set, and these P psi j's are just sort of the unit vectors with zeros everywhere except on the jth coordinates, it's psi j. Okay, and psi j is in the boundary of the ball. Okay, so so these are the faces, and then you can actually write down the homeomorphism explicitly. Okay, so I'm going to give it to you. Yeah, so so first of all, we have to say something what to do with z inside our domain B. Well, in that case, if I look on the jth coordinate of z, well, sorry, on the ith coordinate of z. If that's not 0, then I can draw the straight line and identify this point z prime I in the boundary. And if it's 0, zi is 0, I'll just take it to be 0. Okay, so then actually the homeomorphism should map z well to what? Well, the sum over I of these vectors p zi prime times this constant, which is e to the power the Kobayashi distance in the ith ball between zi and 0 minus e to the minus the Kobayashi distance between zi and 0 in the ith ball. And then I have to normalize this to make it a convex combination. Okay, so this is just a normalizing constant here. Well, it's not to make it a convex combination, it's to make sure I still live in the ball. In fact, this will end up in the interior of the ball because there's a minus here and there's a plus there. Okay, and then for the Horo function h, where h is given in our usual form, we have this j, psi j, and alpha j. So we get the sum over j in j, e to the minus alpha j, p psi j, that's the psi j, and then we have this normalizing constant here. We do need to end up in the boundary of the ball, so we do want this to be a convex combination. Okay, so this can be proven to be a homeomorphism in this case, and yeah, so this is not so easy to do. Well, it's not so hard either, but it requires quite a bit of steps to prove it's all. The idea is basically to show that it's of course you should realize that it's enough to show that this phi is in fact a bijection, and it should be continuous because the ball, well, the Horo function compactification is compact in this case. Yes, it is a compact set, and the ball is Hausdorff, so it automatically then has a continuous inverse. So we only have to show that this phi is actually a continuous bijection from the Horo function compactification onto the ball. Okay, so okay, so now let's go over the case of the Hilbert geometry, and as I said, I'll focus on this domain of these n by n Hermitian matrices, positive definite ones that have trace n. So first of all, you can ask yourself, what on earth does the dual ball look like at all here? And here, of course, I want to take my base point to be the identity, where we had this nice expression of the Horo functions. So, okay, so what does it look like? Well, I should say there's because of the Jordan algebra structure in this setting, there's very nice theory one can use, and then I'm not going to explain any of it, but I should emphasize that actually lots of things that I'm saying here in this explicit example have direct analogs in this general framework. Okay, so first of all, what's the tangent space? The tangent space, of course, all trace zero matrices, and the norm there is just the diameter of the spectrum of a matrix. Okay, and then to express the dual ball, well, there's some nice tricks to do this, but in fact, what we can do is we should look at what is called the state space of this Euclidean Jordan algebra. So what we have is we have the state space are all those positive semi-definite Hermitian matrices which have trace 1. Okay, and so these are the well, I guess if you do some C-star algebras or so, you would say if you apply the function, the unit, if you apply this functional to the unit, you get 1. I mean, this is like saying that the trace of B times the identity matrix is 1. So the dot product between B and I is 1. Okay, so this is what is called the state space. And what I can do is I can take the state space and take the union with minus the state space. And I take its convex hull. So that gives me a nice solid ball in the space of n by n Hermitian matrices. And I blow this ball up to get with a factor 2. So I give it radius 2. And then I intersect this with this tangent, with this space. And that intersection, that actually gives exactly this ball. Okay, so that's useful. So let's also talk about the parts of this metric space, this Horo function compactification. So to explain that, again, there's a bit of terminology needed here. So as I said, the Hermitian n by n matrices, they form Euclidean Jordan algebra. And so there's a cone of squares in there. And this is actually the set of matrices that have all its eigenvalues non-negative, so positive semi-definite matrices. And this cone induces a partial ordering on the space. We say A is below B. Well, if B minus A is positive semi-definite, or B minus A is in the cone. Okay, so that's the notation here. A is below B if B minus A is positive semi-definite. Now, suppose we have two Horo functions, H and H prime. And so this H was given with this data B and C. And H prime has data D and E. Yeah, then the Horo functions H and H prime are in the same part if and only if, well, B and D are comparable and C and E are comparable, meaning that there are constants alpha and beta, so that if you can scale B down to bring it below D, and you can scale it up to bring it above D. And the same, you have delta and gamma, and you can scale C down to bring it below E, and you can scale it up to bring it above E. And geometrically speaking, it means that actually there's this cone of positive semi-definite matrices. These matrices B and D should be in the same relative interior of a face of this cone, and the same for C and E. They should be in the same relative interior of a face of the cone. And in fact, you can compute the Hilbert, the detour distance, which is actually the sum of two Hilbert distances, namely the Hilbert distance between B and D plus the Hilbert distance between C and E. Okay, so you can explicitly compute this. Okay, so now the homeomorphism looks as follows. So, sorry, my homeomorphism is phi h here. So take any element in your domain, in the interior of it, in our metric space, then we should map A to A over the trace of A minus A inverse over the trace of A inverse. And the Horo, if I now look at the image of a Horo function H, where H has the usual data B and C, then actually it should be B over trace B minus C over trace C. Okay, and so this map you can show is in fact a continuous bijection from the Horo function compactification onto the dual unit ball. And it maps parts to parts. So or it maps parts to these relative interior of the faces. Okay, so so this of course begs the question, what about more general things? So here's what we can do so far. So this is based on joint work with my PhD student Kieran Power and some other work I did earlier. And so first of all, for complex domain, we know it's okay if we can take a product of domains where these BIs are actually open unit balls of some norm, where the BI is strongly convex and has a C3 boundary. And this can probably be weakened, but I need some results by Abati to basically show that all my points are Busemann points. Okay, and then, of course, the natural question is, and I think that's a really nice question, is suppose we consider bounded symmetric domains with the Kobayashi distance, and we take its realization as a unit ball in a JB star triple. So this is the Kaup realization of any bounded symmetric domain is holomorphic to a unit ball in a JB star triple. So again, you have Jordan structure there working for you to actually help you maybe identify the Horo functions, these parts, the D2 distance, etc., to actually get a grip on this problem. So that's, I think, a nice problem. So for normed spaces, well, I should say in that case, the problem was already posed by Kapovic and Leib, although they didn't talk about parts or anything, but I think they had a sense of this partitioning in another way. I have to admit, I don't fully understand the content of their paper, but they posed the same question, and it was proved by G and Schilling for polyhedral norms that you indeed you have a natural homeomorphism to the dual ball. And then what we could do is we could prove this for Euclidean Jordan algebras, but not as an inner product space, obviously, but with its spectral norm. So it's these are the finite dimensional JB algebras. But okay, and then for Hilbert geometries, we could prove it where we take a symmetric cone and we slice it with a hyperplane. This is exactly what we did in these Hermitian matrices. And so we could take a hyperplane section of a symmetric cone and just get the homeomorphism. Okay, so so I guess what does this all amount to? Well, first of all, there appears to be in some settings a relation between the Horo function compactification of a smooth manifold with a Finsler distance and the Horo compactification of the norm in the tangent space. Yeah, and of course you can ask, when is it the case that if you have a smooth Finsler manifold, yeah, and suppose you have that the tangent space at the base point, at the point B, is a norm, when is there a homeomorphism between the two Horo function compactifications? Meaning, is there a homeomorphism between the Horo compactification of M and the Horo compactification of this normed space, which maps parts onto parts? Yeah, and that would be nice because it would allow one to study actually the Horo compactifications of these manifolds by just looking at the Horo compactification of normed spaces, which is better understood and more accessible.
Could I ask a question?
Yes, sure.
This is something that's been confusing me at the level of the questions you have asked. Examples are clear. So the dual ball is a simply connected set. So is there the adjective simply connected missing from the questions? Because the way you've posed it, if M is a smooth Finsler manifold, etc., etc., etc. But the homeomorphism that you wish to establish is with respect to a dual ball. So am I missing something?
Yeah, maybe I should go back. Okay, so the point is, of course, you're right, as I said before. So first of all, any ball in an n-dimensional normed space is, of course, homeomorphic. However, the requirement comes in to the fact that it should map parts to the relative interior of the boundary faces.
No, I have a much more basic doubt, which is that the basic part of the question is a homeomorphism between the Horo function compactification of M itself and the closed dual ball, right?
Yes.
So now I'm not interested in the duality. I do understand why you're insisting on the duality, but in a finite dimensional space, any ball is simply connected. So do I understand that?
Yeah, so this is a question. So this is, I mean, let me put it like this. All these questions are completely open. Okay, so
oh, I get it. So what might happen is even if M has some topology, one of the things that the question is saying is that when you pick up the Horo function boundary, then some loops are killed off.
what am I saying is you're actually still adding a sphere at infinity in these cases. So the global topology is really that you've added a sphere of an appropriate dimension at infinity, and this is not at all clear, not even in the normed space setting.
No, but hang on. If you take an annulus,
let me put it like this.
Yeah.
I think I'm going to preempt your question with another comment. So first of all, it should be said here that my questions are indeed very general, and it's likely that in this generality, things are definitely not working out. So first of all, in all the spaces that I've considered, the norm, well, basically the infinitesimal form, yeah, it's sublevel 1 set. Basically, it's a convex set, but actually its facial structure does not change.
Yes.
Okay, so there's some homogeneity in its facial structure there that is absolutely required because, well, it's not clear whether it's required, but like in a Hilbert geometry, like a polygon, actually you could have points where actually the norm in the tangent space has a different facial structure. So you can deform like an octagon so into a square.
Right.
Okay, so a priori, this might depend on the base point B. And maybe it's good to make an assumption that actually the infinitesimal form has some homogeneity in terms of this facial structure. Okay, that this polygon, this convex set we get actually has the same facial structure. It might deform a bit, but its facial structure doesn't change. Okay, and in that setting, you might be able to. Then it should be independent of the base point. Okay, that is maybe what one could try. I'm saying we're far, far from answering this question. I'm just trying to indicate that there is, I think, a phenomenon going on which requires deeper study. So maybe I should thank you all and then take questions.
Yeah.
Are you aware of Ethel Schilling and Anna Linart's work on this kind of question for symmetric spaces? They have a paper on that from 2018. It should be interesting to look at it. So it's related to the Carton or the competition.
Sorry, I couldn't.
It partly answers your question in the case of symmetric spaces, in some symmetric spaces. Of course, again, the norm is projected.
Yes, so that's why this, so these questions, okay, so I should say here in the Hilbert geometry setting, these symmetric cones, actually, you have this homogeneity condition. Obviously, in normed spaces, it doesn't even depend on in the tangent, each tangent plane, we have the same norm. In these bounded symmetric domains, yes, you do have your isometry group. You can, yeah, you have.
I'm not talking about bounded symmetric domain. I'm talking about symmetric geometry.
Okay, so.
This is some kind of Lie group where you have a subgroup acting on it for compact at least. This is the kind of symmetry.
Okay. So yeah, you say that's work done in this direction?
Sorry?
It's very hard to hear you actually. So
It's Ethel, Schilling, and Linart. We did it in 2018. Quite interesting. Because of course, shielding, so there is some kind of idea that shielding is using again, and that's why the norms are qualitative. But nevertheless, it's a setting little bit different than what we were talking about. So it is quite interesting and it answer your question in that case.
So the
metric spaces, not symmetric domains, symmetric spaces.
in symmetric spaces, yes. Yeah, I think. Yeah, I'll have a look at that. I haven't actually read that work. Yeah, it might well be that you could take a Finsler symmetric space, because like these Hilbert geometries, that's a Finsler metric and it's a Finsler symmetric space. And so maybe there is something general there. But you think they work really with such a broad Finsler class of things? I mean, yeah, I would be. Anyway, I'll have a look at this. I'm not aware of this this work, but my experience is that often when people do Finsler things, they require a certain amount of smoothness still of the.
Smoothness. That's interesting. Thomas is a metric guy as well, so he's a very clever guy. You should have a look. There's a word that I think it's quite interesting for us as well. The ideas are different than what we used to.
Okay.
That's what I'm saying.
Thank you.
Okay. Any more questions? So, Gautam. Gautam.
Yeah, I'm unmuted now. So, Bas, this is a little bit speculative because I have no idea of any canonical Finsler metric that goes together with a projective toric variety. But when you were talking about this correspondence between parts and faces, I was reminded of these very cute objects which somehow naturally seem to have what you described in your examples to be like parts. So as I said, this is speculative because I don't know enough to know if there's some kind of a canonical Finsler structure. But is anything known about toric projective varieties in this direction?
Well, I'm no expert in this algebraic geometry, but basically what G and Schilling showed is that these Hor function compactifications are actually corresponding to certain toric varieties, yes. And yeah, so there's a link between, for the polyhedral norms, there's a link between toric varieties and Hor function compactifications. That's actually the content of this paper. But it explicitly, actually in a preprint, they proved.
I see.
This thing.
Oh, so, interesting.
So there is, if you're interested in that, you should actually look at the work by G and Schilling. Yes.
Yeah. Oh yeah. Okay. Hearing it for the first time. Right. Yeah. Thank you.
Any more questions? Yeah, Bob.
So, Bas, thank you very much for this very nice talk. To me, it was really interesting because I read about this. So, exactly in this slide, so you prove the result for strongly convex domain, and then the natural question is what is missing for strongly pseudo-convex domain? I mean, I guess that here you use that autosphere for strongly convex domain. They exist and so on, right?
So this. I mean, I'm really no expert in all this, this subtleties about these domains and the smoothness properties. But I use something quite crude, just a result from Abate's book, just to make sure that I get all points are Busemann, and then that way that you get actually that any two Busemann points have infinite detour distance, and so there I need a strong convexity and C3, and I need also basically on each of the components that the identity sort of extends as a homeomorphism. So yeah, I think the experts could probably easily generalize this statement for complex domains. But yeah, I'm more interested in actually going to bounded symmetric domains. So that's where I think something interesting could happen. Yeah.
Thank you. Thanks. Any more questions? If not, then thanks once more. Are having a coffee break, and we'll see you in 35.